Welcome everyone. Today's topic is sequence alignment. Let me start with an introduction. Why do we need sequence alignment? Or in general, why do we want to compare two sequences? In biology, we want to understand different patterns of variations in the sequence, and these patterns and their variations allows us to understand the genetic causes of the diseases. Hence, comparing two sequences provides us the changes happens in the sequence during the disease. So that's the one reason we would like to compare two sequences or align two sequences. Taken this example, here we can compare a reference sequence with a sample sequence, and when we see that at this particular point where C is changing to A, so we can identify a mutation or a set of mutations in the sequence in a particular disease. Another reason in the biology we are interested to identify the conserved region present in the sequences. Why do we want to actually identify conserved regions in the sequence? Because we want to assess the sequences and figure it out that a sequence or a set of sequences are sharing a common ancestor. Take in particular this example, I have three samples coming from a different sequence, and you can see that this is the common or identical regions in all these sequences, and it helps us to identify this is the region which is getting conserved throughout these three sequences, and hence I can go back and see whether there is a common ancestor to these particular organisms. And of course, one of the main idea of sequence alignment is to search for sequences in a databases that are similar to the one we have right now, or we have actually sequenced using unknown sample. So these are some of the reasons we want to compare the sequences. So how can we compare two sequences? A sequence alignment typically perform two tasks: construction of the best alignment between two sequences and assessment of similarity from the constructed alignment. So when we want to compare two sequences, first we have to construct best alignment possible and then see how this constructed alignment is similar by some set of assessment. There are two kinds of alignments are possible. One is a global alignment and another is a local alignment, where our question of construction come into play. So I can actually do global alignment versus local alignment. Both of them have their own applications. So we'll look at first global sequence alignment. So what is a global sequence alignment problem? Here the problem is to find the best possible alignment over the entire length of two sequences. Having said that, very natural question comes to us that when should I perform global sequence alignment, or when should I formulate, given two sequences, a global sequence alignment problem? Typically, global sequence alignment problem is formulated between sequence of comparable length with significant degree of similarity throughout the sequences. So if I have a sequence or reference sequence and I have a sequence from other suspected organisms, then I want to actually compare them, because I might find out that most of the sequence are throughout my two sequences are aligned or more or less similar. There might be some different path. So one of the example of global sequence alignment is if I have sequenced an unknown organism and I would like to see that this unknown organism is similar to one of the organism available in the reference. In that case, it is highly likely that both of these sequences throughout have a larger similarity with some small uh, dissimilarity, or some part of the sequences are dissimilar. In that case, global sequence alignment is formulated. Let's take a single example of what does it mean by base global alignment. So I have taken two sequences. First one is a Saturday spelling and another one is Sunday spelling. And what I am looking for is the best alignment between Saturday and Sunday. Remember that both of them are not the same length. This one is length 8 and this one is length 6. And I'm going to actually create a global alignment between them where I have S compared with S, A with gap, T with gap, U compared with U, R is basically is not aligned, mismatched, D with D, A with A, and Y with Y. So I have here three kind of possibility. One possibility is A with some gap, so I'm not aligning any of my character or letter to A. So I'm putting this as a gap. This symbol here is a gap symbol. Another one is mismatch. Here the R is aligned with N. Now question is why I am allowing mismatch. By allowing mismatch, I allow other letters to align with the same letter. Here D is aligning with D, A is aligning with A, Y aligns with Y, and this is called, all these remaining are called matches. So I found a match for S with S, U with U, D with D, A with A, and Y with Y. Hence, in any sequence alignment, we have a three possibility: match, mismatch, and gap. We'll talk about this later, some point of time in this course, how we actually manage between them. But we'll go next to the local sequence alignment problem. So what is a local sequence alignment problem? Local sequence alignment problem is finding the best possible local alignment over the entire length of two sequences. Remember that I am looking for some local alignment, not a global alignment. Why do we need to actually perform local sequence alignment, and when do we want to formulate a local sequence alignment problem? If I am comparing stretches of the sequences that are shorter than the entire sequence, so I have two sequences, or I have reference sequence and I have some shorter sequence, and I want to know in this reference sequence where this particular shorter sequence can align. Then in that case, a local sequence alignment problem makes sense to us, and we would like to formulate this problem as a local sequence alignment problem. Remember that I have two sequences of different length. One might be a very, very large length, and I have another sequence which is a small or a fragment of large sequence, and I want to see how it actually align with the larger sequence. Where it is useful, it is suitable when we comparing sequences of widely varying lengths. So one is like say 1000 or 2000 and one is 100. So it's a widely varying, almost 10 times, 20 times. And you will realize that this magnitude will go larger and larger when we discuss this or real sequences, particularly human genomes or other genomes. Other reason we want to do is to compare sequences that share only short patches of similarity. So I want to actually find out two sequences where they are dissimilar, but there are some similarity. So as a short patches, so there will be a similar patches, then there will be different and different patches. In that case, global alignment problem does not make sense. I would like to understand that what are the similarity between these sequences locally rather than globally. In that case, local sequence alignment problem should be formulated. Let's take an example of best local alignment between sequence sweating and eat. Remember that here this particular one is again length of 8, this is of 3. If I try to find out a base alignment between these two, you can see that it will align with it and it. Of course, I can formulate this problem as a global sequence alignment problem, and in that case there will be gap, 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 except when we match E with E, A with A, and T with T. Hence, I would have a problem in terms of S, W, I, and G because I am not aligning it. And if I give a certain negative score to the gap, then this alignment is a kind of poor alignment. Also, application point of view, sometime we are not interested in finding out the global alignment, but we want to find out what is the similar patch of sweating with the it in general. So in those cases, local sequence alignment problem makes sense. Now here, try to compare between global and local sequence alignment. I also talk about score. So we'll try to see what is the scoring in alignment. Okay. So let's start with the simple question of why do we need to assign a score to a given alignment. Simple reason is, how do we decide the goodness of a given alignment? If I give you a alignment, how do you decide whether this alignment is good or bad? Particularly when I'm looking at a larger sequences. Smaller sequences are good, but often we are interested in practice larger sequences, and I cannot go through them letter by letter to see whether they align or not and keep a track of it. So we have to provide a score to figure it out, the significance of how well the sequence or set of sequences is aligned. So what is the scoring scheme we can use? So simple core scoring scheme is following. For each nucleotide, we provide a score. So score for each possible nucleotide alignment. If you recall, nucleotides are A, C, G, T normally. And what we are looking for is providing a score for those alignment between A to A, G. Let's say take example A, G, T, C, G, and I have another. So here I'll provide for each alignment certain score and some penalty for the gaps. Why we provide penalty for gaps, we will discuss later on. So for each one, I'll provide some score, match, so for match some score and mismatch some score. And typically the alignment score between two sequences is sum of all these individual scores for each of these nucleotides and the gap penalties. Let's take a simple scoring. If there is a match, I will provide a 1. If there is a mismatch, I will give a -1 score. And for a gap, I am not providing any penalty, keeping it equal to 0. And I have an alignment here. So I want to provide score to this alignment. So here we can see 1 match, 2 match, 3 match, 4 matches, and 5th match. So I have 1 plus 1 plus 1, 1 plus 1, 5 match. I have a mismatch, which is CA. So I have minus and 1 gap, which is equal to 0. So it has -0. So I'll get my alignment score. So let's see what is my alignment score. So my alignment score is 1 plus 1 plus 1 plus 1 plus 1, which is 5 alignment, 0 for gap, and -1 for mismatch. So my score for this alignment is 4 based on this scoring scheme. Now, this is a little simple scoring scheme. We have to look at the practical scenarios. In many real world, the simple scoring scheme are not that much useful. So we have to go for a more realistic scoring scale. Score that does not reflect the physical frequency of mutation rates between the different nucleotides are not typically used. So we want to actually ensure that when we provide the score, it reflects certain physical meaning. For example, in mutation, it's more likely to change from one pyrimidine basis to another pyrimidine base or base rather than purine. So pyrimidine bases will change to pyrimidine bases, purine will change to purine, but pyrimidine to purine is rare. And of course, it may have some implication in certain diseases. So the realistic scoring matrix, which can reflect the physical relationships or physical phenomena, typically people use a scoring matrix where if C and C alignment we give a 2 as a match when we match it, but C to T mismatch will not find much, we will actually give a 1, while C to A or G we can give -1, -1, because this mismatch is not physically possible, so we give a or physically rare, so we give them as a negative scoring. So similarly for T, A and G, we'll look at it, the score such that it reflects the physical relationship or physical phenomena, which we often observe in the practice. Now let's come to the gap. The gaps we have assigned so far score of 0. But in general, gaps should not be assigned score of 0 because it has a more ramification. Let's understand how gap can be created or possible way of gaps. Gaps can be through the insertion or deletion of nucleotide. So take an example here. So I have this is sequence ATCC. Instead of that, I have a ATCTC. Okay. So there is a new insertion is here. Or in a simple example of boat versus boats, the S is a insertion. or inserted later, which when I try to align these two creates a gap. So for example, in case of A, T, C, 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 T, C, T, C. There is a, because of insertion of T, there is a gap when I align ATCC with ATCTC. The another possibility is deletion of nucleotide. For example, here the ATCCC sequence become ACC because there is a deletion of T. Or a simple example of Bhatt to the Bhatt, the O is deleted. And you can see that Bhatt become Bhatt by just deletion of O. Similar kind of implication might be there in deletion or even insertion. Hence, gaps sometimes are more worrisome than the mismatch. And that's why by convention gaps are assigned a penalty magnitude greater than the mutation penalty or mismatch penalties. Why? I'm going to give two reasons. First reason is it interrupts the entire DNA sequence. So sometimes very difficult to get an alignment if we do not do a gap more penalties. Or if we ignore gap equal to 0, we get a sequences which are not biologically significant, and it creates more problems when we try to do downstream tasks based on these alignments. Hence, the gaps are considered to be a bit more problematic than the sometimes mutation, and hence we provide gaps more or greater amount of penalties than the mutational penalty. Now, penalizing gaps, there are two ways we can penalize the gaps. We'll see the significance of both of them in the coming slides. First one is the constant gap penalty. So, we provide a constant penalty for each gap. We do not worry about whether it happens consequently, means one after another, or happen rarely. We apply constant gap penalty. And to mimic or to resolve the real problems, what we need to do is to use another kind of penalty which is called affine gap penalty, and we'll see why affine gap penalty is useful. So affine gap penalty is scored in following manner. I will look at number of successive gaps. So remember, in a constant gap penalty, successive gaps have a same kind of penalty. However, in affine gap penalty, we look at successive gap. The opening gap is designated as a O. A subsequent extension of that gap, which is rest n minus 1, are given designated penalty of E. So, the penalty score for the affine gap, we give certain penalty for opening and then subsequent penalty for extension. And then total score for affine gap penalty is O plus n minus 1 into E. And of course, remember that this is penalty, so we assign a negative values rather than positive values. So let's see the difference between constant gap penalty versus affine gap penalties. I'll take an alignment. So this is an alignment, and I have aligned this sequence with this sequence in this manner. I'll give a score matches 1, when A matches with A is equal to 1. Mismatch I'll give minus 1 and give gaps as minus 2. See here, I do not have any mismatches. I have a match and the gaps. And if I count the score here, it will become minus 8. Right? Okay. So you can just do the summation and count the score like we did it last time. Give each one a 1. If it's match, -1 it is mismatch, and gap -2. So this particular alignment will give a -2 and henceforth. Now the question we can ask is, can we align them better? This is one alignment, and with this score I got final score of -8. Can I do better than this? Can I find a better alignment which actually reduce this score? Let's use a fine gap penalty to align these two sequences. So again we will take the same alignment, but I am using a fine gap penalty to align these two sequences. And if you look at it, now I have sequence which is aligned with this way, there is a huge gap, and then I am aligning. Okay. So here again there is a little bit change in the score. So for opening gap I will provide the score equal to -2, which is equal to the constant gap penalty. However, extension gap I will provide less penalty, means -0.5. Remember that affine gap penalty helps us to create a more biological significance sequences. And if we do this way, then the final score of this alignment is 1. So what I am doing is, let me explain again in more detail. This one and this one, this one sequence, this and this alignment, which are match alignment, I am providing score of 1. Now I have the opening gap. This one will provide -2, and remaining each of them will provide -0.5. And the summation of all this together, so I have a 6, 7 minus 1 into -0.5. That's the score for this particular extension gaps. And if I sum them, the alignment score will be 1. And this particular alignment makes biological more sense, because it's possible that this particular part of the sequence is indeed removed. So affine gap favors this kind of alignment instead of the constant gap penalty, which was actually giving several intermediate gaps, while in affine gap penalty we get a gap which is successive. And this particular alignment makes, as I told you, more biological sense, as it more likely for a region of DNA to be removed than a multiple removals. So as we discussed, it is possible that complete region of DNA can be removed rather than in between the region got removed while we actually sequence it or while we do the processing. Hence, affine gap alignment will be used providing penalty for gaps.